Like that, share it again. Let me put this up and get this here. Uh, Hassan has a question. Let me address that. So, would you be able to speak? Would you be able to unmute yourself and speak, Hassan?
Good evening, sir.
Good evening.
Sir, actually, the outward key provide some booklets for formulas.
So,
Which are
Hassan, no, I don't think I can hear you properly. Though I have read your message, let me talk on it and let's just type out your response in the chat only. It seems that's the better of the options. Okay. So his primary question is on the booklets for formulas. Uh, so Hassan, may I know what background are you from? Are you which engineering background do you have? Like which department are you affiliated with? Okay, so you are a mechanical engineer. So that's the good part. Uh, let me- a lot of these things. Okay, so now, yeah, I have to share the screen, right? To share it. So this part, let me open up. Right. Okay. So about the booklet, what I would suggest to you is, see, I have been referring for my thermodynamics. I've been referring this book by Senger and Bowles, Senger and Gazar. So let me share, open up that book for you. And any, does not matter actually. You can pick any book for that matter. And so essentially, these books will have these chapters, right? So the first chapter is on introduction, then the other chapter is on energy, and then the general energy analysis. I think this is for the open system, or maybe overview, just an overview of first law, right? Here in the fourth sem. Okay, got it. So now, so these are these chapters that they will go, and primarily this is what professor must also be following. Now, if you refer to these books, generally, they summarize the content of the chapter towards the end, and you will have all the formulas that you would need. Uh, if you could help me understand what formulas you were having trouble with, or what essentially. So, for example, in this chapter, see the summary kind of uh, has all the formulas that essentially are referenced or talked about in this chapter. If we go to the chapter number two, read for the numericals in your what do you say in your second assignment. So see like this. So I'll just zoom it in. So you'll have these formulas, okay? Right. So all these formulas will be available generally in what do you say in the summary of the chapter. But I would quickly like to understand essentially if you can type out what formulas were you having trouble with. Okay. So just to understand what was non-intuitive about these formulas, just to understand that part of it. And just to add on that, I actually saw your mail. I did grant you the access to the drive folder. Although I have not uploaded anything yet on the folder, I will upload these lecture files, PPTs there. I'll do that, and I'll also reply to you by tomorrow, I guess, or late tonight. Okay. So if you can type out, yeah, you have messaged me. Okay, so roughly is that does that mean that you're queries addressed, or would you like to tell me what formulas were you having trouble with to quickly talk about that part of it also? Like I could quickly talk about those aspects so that it becomes clear to you and you essentially don't need formulas per se. So, for example, I don't refer to these formulas. I kind of have memorized them, internalized them already. So maybe I can also help you do that before, like, so you also don't need these formulas as such, because these are very straightforward formulas. You like you see, right, for efficiency of motor or efficiency of generator. If you go on, like, the only reason you would memorize them is you don't have an idea why are they in the form they are in. So just I can give you an intuition about that if that is what you're essentially concerned about. If no, then we can move on. This one here. Okay, so you have messaged me something. Let me check. Okay, you understood. Fine, fine. You're still typing, so I'll wait for your thing.
Good evening, Shreji.
Good evening. Good evening, Jyoti.
Meanwhile, sir, can I ask one question? I have one doubt from the previous assignment.
Yeah, yeah. Please go ahead.
Okay,
Please
okay, sir.
go
I will
ahead.
share it in the chat.
I can hear you well enough, so maybe you can speak also. That's okay. I think I can hear you properly. Yes. So just give me a second. I am trying to access all the problems that we are going to discuss today. Okay. Then I'm just logging in. Meanwhile, as Jyotirmay is going to ask her doubt, so let's wait for that as well. So, yeah, he's typing. Anyways, hmm, let me type then. So he has pushed her. Okay.
So basically, this was a question. Sorry, I have shared my question.
Mhm.
Yes. So this is the question that was there in the week 2 assignment. So in this, I had given the answer as 2 sigma BL, and that is also in line with the uh, what was taught to us in the and in sir's book also. It is like sigma DA and DA is 2BX. However, the final answer was given as sigma LB. So so basically, if you can please
Let me.
explain.
Yeah. So a U-shaped wire frame with a slide wire S. Okay. Wait, a U-shaped wire frame with a slide wire S, as shown in the figure, is merged into the soap solution. A soap film is then formed in the wireframe by moving. I understand. 2 sigma comes from the two sides of it, isn't it?
Yes, yes, sir.
Right? Note
Yes.
that F is the constant force applied to move the slide wire, and sigma be the surface tension. Determine the expression for finding the work to overcome the resistance offered by the surface tension. So L is this, LB is the area, and sigma is what? Sigma will
Sigma is
be
the
what?
surface tension.
Surface tension. F will be what? Sigma B, right? No.
If is force, yes.
F will be what? Sigma, I don't know. Sigma. So It's 2 sigma B, right? 2 sigma B into A. Okay. Yeah. So
So,
see, the thing is with these questions on NPTEL, na, you can quickly write to it. This seems to be a correct thing. Okay. 2 sigma LB seems to be the correct option. Okay. And this is something that you can just quickly ask them if this is a like error in their marking scheme. Okay. As you have also referred to the book and this seems to be correct, right?
sir, to whom should I ask, sir, then in NPTEL for communication?
Okay, that's a good question. Let me see. That's a good question. Whom are you getting mails from, by the way? You have a mail ID, right? You will have a mail ID, isn't it?
Yes, so that is my mail ID, and on that I get the notification from Swayam itself. But there is no person like that in loop. Of course, you are there for the doubt clearing classes.
Okay. So there are actually two guys. There are generally two these are two TAs. The your assignments are essentially dealt with a different TA. So he sets the questions and he is actually also so evaluation happens all automatically because it's a multi-objective thing. But let me just so that is why I'm not the concerned person as such. But let me quickly see if who to address. That's a good question. Also, quickly you can mail them and ask them if the question, what is the issue with the question? Because clearly the answer is correct. That happens most of the time. I have seen multiple cases of that. Okay, so yeah, we see. Yeah, so you can mail them here. Let me put this up in the chat.
Okay, sir.
This should help. Okay, let's see. So this should help. You can copy paste this because generally you won't have access to the chat after the call gets cut. So that is also something that will happen. Okay.
Okay. Thank you, sir.
Any other thing? Any other thing? No?
And so, yes, sir, just one more point. I'll
Mhm.
just share. That is, sir, just a moment, sir.
Yeah, take your time. I will wait.
So I just
You
copied
can
it.
ask.
And
You can
thank you, sir, for sharing this. And sir, just one more thing that again, just share the picture. So,
You've shared anything, is it?
yes, I have just shared one more photo. So this is one of the lecture slides from sir. So I have
Let it. Yeah, it
yes.
is gonna
Okay.
come with you.
So over here, it was been stored that for any process, the number of the thermodynamic properties, independently variable thermodynamic properties, is equal to number of reversible work modes plus one. So can
Hmm.
there be an example where we can have a reversible work mode, let's say 1, 2, or 3 like that? I just wanted to understand.
Okay, let me just read this part. Not come across the term as number of reversible work modes. Okay. So for a given number of independently variable, what is TD?
So thermodynamic. In the blue line, it's given the thermodynamic independent variable properties
Is equal to number of reversible work modes plus one.
plus one.
Okay. So for
So
us is simple. Hmm.
maybe I can share the lecture slides also. It is there.
No, it's okay. It's okay. I understand what they mean.
Okay, sir.
Okay. PDV number of TD is 2 is required for complete description of the system. Okay. If I understand correctly, let's figure this one out together. If I understand correctly, see there are a lot of reversible work modes, right? This is what they would mean generally. And your question was? What was your question, if to be precise?
Uh, Sir, suppose I have one function, let's say from point 1 to point 2 on the PDV diagram. So I have one curve,
Mhm.
right? So so area under the curve is like the work in the PDV diagram. So I can say that is equal to one reversible work mode. So can there be any example of where the number of reversible work modes involved is more than one, like two or three, like that?
Okay, okay. Is that is your question, right?
Yes, sir.
So what other reversible work modes are there?
Yes, sir. Maybe with some example. So, for example, if I have an auto cycle, so in case of an auto cycle, we know that there are four steps. Like initially, we have isentropic compression, then constant volume heat addition, then isentropic expansion, and then again constant volume heat rejection. So, in this kind of example, then the number of reversible work mode, it should be equal to one or four, like that.
No, it will still be one.
One only. Okay.
Uh, it will still be one. So the way I understand this statement is, see, another reversible work mode will be electrical work. Say your voltage potential across which some current is coming is close to, yeah, it's some value, but it's reversible. So electrical work is not reversible, right? Reversible work mode. Let me check what it means. See, I'll tell you why. What do they mean? See, I'll tell you. Uh, simple compressible. Simply compressible is the term that people use. Okay, you heard about simply uh, they told you about simply compressible systems, right?
Yes, yes.
Sim- Right? What is the definition of simply compressible? Let's go to there. Let's go there. Think it's simply compressible only, right? That is what the slide also says. Simple compressible system. Should be some, yeah, here. So a system is called simple compressible in the absence of electrical, magnetic, gravitational, motion, and surface tension. So if I give you an example, let's take a very simple example of gravitation. Right? Gravitation is something that we can quickly, like it's very easy to understand. Suppose there is a gravitational work, or like there is a gravitation also important in our system description. Okay, let's say height of a system. Uh, See, height is also a state variable now. You understand? And
Yeah.
this will itself give you another work done, right? It will give you a another, what do you say? Another state, and that state will give you another work. So work done on that, like another work mode, reversible work mode, will affect this additional state variable. In surface tension example, what do you say? The area of the stretched or whatever, the surface area of your system becomes another state variable. This is what I think the statement means. Okay, let me also quickly verify that. For magnetic for magnetic, let's look at what is what do you say? What is the magnetic work? Okay, we quickly check what magnetic work is. Magnetic something. This, yeah. So in the case of magnetic work, these are non-mechanical form of work. Where this part? This is okay. So even in shaft work also, if you think about it, shaft work also gives you another state variable. Does it? Let me think. Shaft work gives you another state. It should give you another state variable, by the way. Even in spring work, let's say spring work, the additional stretch. What do you say? If your system is a spring, let me give you this example. at least this is what I think the meaning of the sentence is. Let's say we have a system, we have a piston cylinder system, and there is a spring attached to it. Okay, let's say there is a spring attached to this system, right? Something of this sort. Like, I'm just quickly drawing things. Uh, Now in this case, volume gets associated with the state, this how much is the spring attached, stretched or not. But in a, let's say this spring is not constrained to some wall. Let's say the spring is not connected. Okay, in a constrained case, two state variables become dependent on each other. But in an unconstrained system, in a general system, if my system is composed of a compressible part, a simple compressible part, and a spring, so the spring, the length of the spring becomes another state variable. You understand? And let me quickly check this part. So, what does that this statement mean? Because I've not come across this statement before, but let
So
me.
should it be
This
the
I
length
think
or the stiffness? Sorry. Should it be the length or the stiffness of the spring?
no
As it,
stiffness is a constant, right? Uh,
okay,
it should be the length, right?
okay. And then F is equal to kx, like that.
Makes sense, right?
Yes, yes.
Concept of reversible work mode refers to how. Let me ask ChatGPT, best guy. Where do I have ChatGPT? Do I have it here? No. Just give me a second, okay? Yeah, it's here. So I will just quickly also read this sentence out to them. So for a given thermodynamic system, number of independent properties is equal to the number of reversible work modes plus one. What does it? And do you understand why the spring constant should not be a state and should be a, what do you say, whatever property of the system? No, it's not a. So why do you understand why the length of the spring is a state variable and not the spring constant?
Mm, well, because the spring constant is will always be constant, but the length it is the variable factor, which will maybe like affect the force or the other dependent parameter.
Right. And what would be a corollary of this spring constant? Say in a like if I tell if we are drawing comparison between the spring and a simple compressible system, what is the parallel to spring constant? Is there a parallel to a spring constant in a simple compressible system? Can you think of any quantity which is similar to a spring constant in terms like in the comparison we are trying to draw? What do you think about the gas constant or the molar mass of the gas it has,
Okay.
right? It molar mass remains constant, and that characterizes the gas, ideal gas, the gas equation, the what do you say, equation of state, right?
Okay.
Makes sense?
Yes.
Okay. So see, even this guy is saying that the work modes are electrical work, surface tension, and magnetic work. And the reason why this is n+1 is gas. Gas will give you P and pressure and volume. But in, let's say, electrical work, electrical potential becomes another, or charge becomes another state variable, as we were discussing, right? In case of spring, we will have so similar lines. So it's kind of saying the same thing. And also something which maybe I can show it to you somewhere. Actually, it says. Let me just quickly pull that up. Total work done is this plus this plus this. Is that there or not? Let me just quickly check that. So in a general system, if it's not a simple compressible system, generally you have to consider all kinds of work interactions that can happen in a system, right? That is the most general expression for work done to a system, right? We generally say PdV because we are considering a simple compressible system. But for a non what do you say, for a non like a, for a general more general system, this is what you will say, right? This is what you will say. So let me write this thing down. But see this statement. Let me first write these things so that we can go one by one. I'm jumping between things. So let me write this first. For a, or let me first write what a simple compressible system is. Okay. What is the definition? Is defined as. But I'm putting quotes there. Let me just pull that part up. As as a system with uh, in absence of electrical, magnetic, gravitational, uh, gravitational motion, and surface tension effects. Okay. Uh, for now, when we write work done, W is PdV. Note that this is only and only for a simple compressible system. For a more general system, what should the work done be? So work done should be PdV plus magnet. So that is V di, I think. What was it? Now I have to go with this. Yeah, let me quickly go. Let me. Hmm. So this will be dq. Okay. Dq. Yes. dq. Which is the charge. Let me put this as charge is Q. Let me say Q. Okay. Then Q is coulombs. Okay. Then you can also have shaft work also present. So omega T. So torque. T is the torque here. Let me put something else. Tau I'll put for torque. D omega. Omega is the rotational speed. So torque work should also come. Okay. Uh, then spring work. Spring is also some work uh, which comes, right? Which is K. This is Kx dx. Okay. So F spring dx. X is the displacement of the boundary. And then you can also have other kinds of work. Magnetic work should also be there. Why is there no expression for magnetic work in this chapter? Let me quickly scan this chapter, see what is the magnetic work. Do we have an expression for it? And so, for example, surface tension is sigma, right? Sigma force per unit area. So there will be a length term, sigma into dA. That's a sigma into dA, right? Then what
Yes.
else? Uh, so there should also be a term for work done by magnetic. Right now, let me write this thing. Okay. Now, see, with every work done expression that you're writing, reversible work done mode, you are essentially giving another state variable. For PdV, there were two, right? For now, charge becomes your so the charge in the on your system will become another state variable. Uh, Omega is the rotational speed it has, becomes another state variable. The length of the spring, let's say, becomes another state variable. So that was the meaning of this statement. Okay. And so on. So this is something that we need to note. Okay. But again, this is a loose definition. This statement that your number of independent variables are one plus this thing is an observation. It is not a law, or is not, it's not a fundamental statement. It's not a fundamental thing. Note that down. This is an inference. We noticed that this happens and we wrote that down. Essentially, the number of independent variables, the number of independent uh, state variables uh, is essentially comes from Gibbs phase rule. Okay. Well, that is also not correct. That Gibbs phase rule apply to a simple compressible system. So maybe we can write the statement. But again, hmm, but anyways, for a simple compressible system, the fact that this n plus one, this why one plus is coming. So for that, actually, Gibbs phase rule is the important. Gibbs phase rule is an important. What do you say? Uh, that is the essential rule which gives you the number of independent. It's not the number of reversible work mode. Essentially, if you have charge and all that is important to you, essentially those will count as state variables. But for a simple compressible system, this plus one is coming from the Gibbs phase rule. Let me put it that way. Okay. And also let me see if Gibbs phase rule is. Did sir discuss about the Gibbs phase rule in the in the video? What do you say? Slides?
Not yet.
Not yet. Okay. So I am unable to find it in the book. So let me find that on internet. It's actually a simple rule. But are you aware of what that rule is?
Yes, the formula that you see that we have studied, F is equal to C minus P plus 2.
Yeah. So when for a simple, now that we have gone into So this was F equals to C plus P minus 2. And actually this comes very well from a very, this rule actually comes very nicely. This is again inferences. We actually derived, this is a derived result. Actually, we can actually see where is this coming from, but that is a little advanced. I also don't remember what the derivation is, but anyways, we can actually quickly understand this formula. F is again, now let's understand what F is in this context. Generally, we call F as the degree of freedom, but for now, let's call F as the number of independent state variables for a simple traceable
Sir, I think
system.
it's C minus P plus 2.
Let me check. C minus P plus 2. Okay, sorry. Yeah. Okay. So now C is the number of components. Now, what do I mean by number of components? Number of species in the system. Okay. Right now, until now, we are not discussing the chemistry of it. We are not saying that the system is homogeneous or not. We are generally looking at a from a black box point of view. But when we are essentially also see again, the composition of your system is also an important state variable. How much composite? So suppose your system has a lot of lot of components, lot of species, or lot of chemicals in it. Oxygen is also chemical. Hydrogen is also chemical. A lot of gases it has. So how much amount of different species it has, let's say normalized percentage of oxygen this system has, percentage of hydrogen the system has, becomes different state variables. You understand, right? You can vary this composition. So C is the number of species. Now P is the phase, number of phases, number of phase. Okay. I'll tell you the interesting part here, why I started discussing this thing. See, generally you have two independent. So generally, let's say if you are a single component system, it's a pure substance. So C becomes one for a pure substance. C becomes one uh, for a, let me also put single phase. So let's say it's in a gaseous phase or liquid phase or uh, what do you say, solid phase. And mind that these are not the only three categories of phases. There are multiple categories of phases. There are other categories also. But without going into the details of what other phases could possibly be there, let's say this is like we are not going very exhaustive on this part. Let's say these are the only three phases we know of, and say that our system can also have simultaneously two phases or three phases. But let's say this is a single phase system, then C comma P becomes C and P both becomes one and one. Then what is our number of independent variable becomes one minus one plus two. So we get two state variables. But in a what do you say? In a two-phase system, which is the now that we have gone into the properties of pure substance, under the saturation dome, we know that there are two phases. At the triple point, we have three phases. So let's look at what happens at the triple point. Let's look at triple point. You know about the triple point, right? Has that part been covered yet?
Yes.
Okay. So at triple point, what do we know? That there are three phases, right? There are three phases, but only one component. So one minus three plus two is what? Zero. So there is no independent state variable. In fact, triple point is indeed fixed. You can actually tell me if you're at the triple point, your all states are fixed. There is no independence. There is no degree of freedom. Okay, that is why F is called degree of freedom also. What happens at in a two-phase region? In a two-phase region, similar thing you can do, and you will find that F will be 1. So let's just quickly see that. And if you think about it, if I think about it, this rule is also coming from that same idea that but like let me verify that part. Where does this rule come from? But essentially, it is kind of coming from a similar thing that your state gets defined completely when and work is one form which can change your state variables. So it's kind of related that way. Okay, but anyways, for a two-phase system, one single phase, a single pure substance, so one component, and there are two phases, so you get 1 degree of freedom. So in that case, either your pressure, once you fix your volume, your pressure gets fixed, and if you fix the pressure, your volumes get fixed. So that is something that might have come up in your lectures uh, this week. Okay. Any more questions? We can discuss those. Anything else? Let me take a break of 2-3 minutes. I'll come back. Okay. Okay, I see something, some comment it seems. Okay, you have any question, Hassan? He's not typing. Oh, he's typing. Wait. Any other question, Jyotirmaji? We're just discussing. Okay, so he does not have any question. Fine. Took a long time to type that, but anyways. Okay, so then let's get on with this. Get on with this part. Okay. Again, let me just quickly check if I can find where this Gibbs phase rule comes. We can check that. Someone. Okay. Let's see this one, 245. Gibbs phase rule comes from this kind of analysis. Quickly check that part for us. It's a little advanced, okay? But anyways, it kind of comes from the same thing, okay? Similar logic. Anyways, let's get on with the problem solving things, okay, for today. So let me put the date for today. Today is 10th of Feb 2026. Let's get started with the first question. So let's start with the easy questions. Chef is cooking mutton stew in a pan that is A, uncovered, covered with light lid, and covered with heavy lid. For which case will the cooking time be the shortest? Okay, so now that you both of you guys have been interacting with me, let's solve this problem together. What are your guesses? And if you have guesses, please also support them with the arguments. Okay. Why do you think A, B, or C? Then the second question also, I'll just quickly paste the second question as well. Okay, so before I solve the first question, let me solve the second question. It's this one is kind of straightforward. So X, or the quality, is generally is defined by mass of uh, so it's 0 at fully liquid and 1 at fully gaseous. So it's vapor divided by total. Okay, so vapor divided by total. See, because this quality is 0 at fully liquid, sub-liquid conditions. When it is all liquid, then this quality is 0, and at uh, fully gaseous conditions it becomes 1. So this is the only correct formula. Okay, this is kind of straightforward. Then now let's solve this chef thing. So what essentially is going to happen, and what dictates the cooking time? Let's discuss that part. So cooking time, first of all, discusses one thing, which is say something requires some amount of heat to get cooked, right? So which will have the least amount of heat leakage? Let me restate the statement and answer this question by saying that for some food to get cooked, it would require some amount of energy, E cook. Okay. Now what will happen if the pan is uncovered? Okay. If pan is uncovered, there will be energy losses from the system through mass. So because the pan will be uncovered, there will be some heated water, let's say, that will escape. And then there will also be an what do you say, heat losses due to convection or conduction. So with the surrounding heat, there will be heat losses with the in form of heat also. There is no work done, right? In this case, there is no work done. That is clear. Are we doing any work? Are we losing any doing any work when we are cooking mutton stew? No, right? There is no expansion, there is no contraction that is generally happening. We have a cooker which is constant volume, so there is no work done as such. When we have a covered with a light lid, what can we say? We can say that mass leakage will be lower. Okay, and with a tight lid, mass leakage will be, let's say, zero. Heavy lid, it says. Now, heavy lid implies what? Now, what does heavy lead means? Heavy lead would not directly imply that there will be no mass leak, like mass leakage will be lower. But essentially, what it is saying is that the pressure inside the see with a light lid also. Let's say, is it possible that there is no mass leakage with light lid? We can also be sure that it is possible that there are no mass leakages with light lid also. But with a heavy lid, what do we know for sure? Yeah, like pressure cooker increase saturation pressure, leading to higher saturation temperature and greater heat transfer. So one thing is correct, that higher saturation pressure is gonna be there. That is the key to the question. So you're saying e-cook now. See, now this is important thing. So let me just, as Jyotirmay ji has typed in, I'll just quickly uh, go ahead and type this thing out. So with this, we know that P cooker is higher, and accordingly, P cooker will also be higher, which implies what? Which implies uh, that largely we can also say, see, I can also say that E cook is proportional to T cooker. Okay, so higher the temperature, we think. So what are we doing? With a lighter lid, the pressure is lower. Okay, but with a higher lid. So what is leading for a heavy lid to ensure that let me think. Okay, so now essentially there is one more thing which is important. See, when we are saying that P cooker will be higher when covered with a heavy lid, we are essentially also saying that mass leakage there might be some mass leakage, will be very low. Okay, so there the energy loss that is going to that is happening will be lesser. So we also need to appreciate the fact that uh, with light lid, what extra energy are we giving in case of heavy lid, that it is not able, like why a lighter lid gives you like why a heavier lid will give you uh, earlier cooking. It should imply that you're giving extra energy in case of heavier lid, right? And that should basically come from that the mass leakages in a heavy lid will be even smaller. So that is the essential idea. But again, the mechanism is through higher pressures and then higher temperature, and that is the logic. Okay, so that is one thing. Let me again quickly move on this thing. Let's get on with the third question. Simple stuff. So is this statement true or false? No substance can exist in the liquid phase in stable equilibrium at pressures below the critical point pressure. Is this statement correct or false? I You guys can quickly answer it. I'll wait. I'll go to the other question. Meanwhile, the fourth question. Let me also quickly pull up fifth question also. Oh no, guys have not responded, huh? Should I wait? Okay, let's look at the other questions before answering this third one. Behavior of a gas deviates from its ideal state under which of the following conditions? High temperature, high pressure, low pressure, low temperature. Okay. And then phase diagram is characterized by which of the following plots? P versus V, T versus V, P versus 1 by T, P versus T. Okay. Hmm. Answers, guys. Okay. Somebody has responded. So Hassan says A, which is high temperature and high pressure. For fourth, is it? You're answering for fourth. For five, you're answering. Okay. So P versus V. You say phase diagram is characterized by following P versus V. Uh, okay. So Hassan, actually, what do they mean? Which phase di I understand what you're trying to say. I kind of relate to you. This question is not very precise, to be honest. But that essentially what do they mean? Which phase diagram they mean is this is the phase diagram. Generally, this is the phase diagram when we say no. It's generally P versus T. I'll show you the phase diagram. Let me quickly pull that up. The phase diagram is generally this one, which we are kind of looking at. Um, this one. This is the phase diagram. Okay. This is see this is the phase diagram. This is what we're looking at. For the fifth question. Meanwhile, also take the time to answer the other two questions. Okay. The two questions you also try to answer that. One more thing. I have a count, like I have a additional question to question number 5, okay? Are you aware of this relationship? This relationship where these two axes are. I'll also share what these axes are, write them more clearly. So P sat, this is the saturation pressure on the y-axis, and this is the saturation temperature on the x-axis. Can you tell me, is this also a phase diagram? Can we call it as a phase diagram? So the idea is this line which you see, right? Uh, uh, so this line which you're seeing is essentially this line. Note that. No, not this one, not this one, this one. So these two lines are the same line. This is the saturation pressure versus saturation temperature line. Just wanted to highlight that. Okay. This is the liquid vapor phase change region. Okay. Okay. Now for Jyotirmay ji has answered that that is false. Would you like to elaborate, or let me quickly do that? Actually, the correct statement is no substance can exist in the liquid phase above the critical region. Okay. So as you can see, this is the critical point. Above it, you can't have any liquid or vapor. The liquid is defined to be below critical point. Note that. Okay. Below critical temperature and critical pressure, liquids are defined only, they are defined to be below the critical point. Okay. Critical point pressure. You can't have, they will not liquefy below, above critical point. Okay. So this one is answered. So this is false. This one is false. Then what about the fourth one? Fourth one, and even fourth one says behavior of a gas deviates from its ideal state under which of the following conditions? Is the temperature high or low, and pressure high or low? So again, as you will see, if you are away from the critical point, if you're very away from the critical point, only in those conditions can you say that assumption is true. And that happens if you have a very low pressure and a very high temperature. So essentially going into this direction. Okay. So run out of space. So we're kind of narrowing down here. So in this region, away from critical point, in this region, so at low pressures and low temperatures. And now how do you quantify the distance between the critical point and this region? You do it in terms of reduced temperature. So essentially saying this. So let me write this down for you. So P divided by P critical should be much smaller than 1. Okay. It should not be comparable to P critical. Only under those assumptions can we say that the gas behaves ideally. And T is again lower than T critical, should be much greater than 1. At this point, I would like to invoke the image that I had talked about earlier. Look at the coordinates of this plot. This y-axis is essentially compressibility, which is 1 when you have very low, when the gas behaves ideally. Okay, for ideal gas, compressibility is 1. Okay, compressibility is defined as Z equals to PV by RT. Okay, now you know for an ideal gas, this follows. This follows. Anybody confused with the fact that what is this NRT or MRT or something? You have different equations. So you know what is the with different equation, what changes in these equations? See, this R gets the way this R, what this R value is, um, dictates what this equation is. Okay. So this generally, if this is a gas constant, which is like kilojoule per kg per Kelvin kind of thing, and so this captures the molar mass effect. So this will absorb the effect of molar mass, and this will be a dedicated value for a particular gas. In that case, Z equals to PV by RT becomes 1 for an ideal gas. And if you will note, that is happening under two conditions. One, at very low pressure. See, at very low pressures, this goes to 1. At very high reduced pressures, let's not look at that part, because we are kind of seeing in the limit, reduced pressure goes to very high. These values will exceed 1. They actually exceed 1. If you look at TR of 2, or let's say any other value, you can actually extrapolate and see that these values are going to be higher than 1. Only in the limit of PR tending to 0, which PR is reduced pressure. So P by P critical, this goes to 1. Okay. And in the very low temperature limit also, and the temperature should also be very high. So you see in this if I would have drawn, so TR is the reduced temperature, T by T critical. You can kind of see that this slope is kind of shallowing down. It is kind of becoming a constant like slope line and approaching y equals to 1 or z equals to 1 line at all reduced pressures at high TR values. So essentially at very high temperatures and low pressures, gas behaves ideally. Okay. Uh, okay. Now let's look at the other questions. So now we have the sixth question with us, which is on the van der Waal equation.
Sir,
Yes, go ahead.
sir, sir, what is the answer for the fourth question? Low pressure and high temperature.
Okay. So this one is low pressure. So these two and then high temperature.
Okay, sir.
Okay.
Yes, sir.
Wait. Wait. See, the question says deviates. Okay. So it should be low. So the it is ideal in the case of low pressure and high temperature. But when will it deviate? It will deviate at low temperatures and high pressures. So the answer to this fourth question should be the D option, low temperature and high pressures. Just the opposite of it. Okay. Is that clear?
Yes, sir.
Right. Okay. Great. Can see or I can hear you properly, it seems. Nice. So, anyways, let's look at the sixth question now. The van der Waal equation of state was proposed to improve the ideal gas law and is governed by the following equation. Which of the following statement is correct? The constant A is related to the volume occupied by the gas volumes, molecules. B is related to intermolecular interaction forces, and the constant B is related to the volume. So which one is the true statement? The truth statement is this: B is related to the volume, and A is related to the intermolecular forces. This is a kind of a textbook thing. You just need to know it. Um, yeah. There's a also a statistical picture of how A and B all comes in a kinetic theory of gas, but we won't go into that because this is a classical thermodynamics course. Anyways, but this is the correct statement. Okay. Now let's go to the seventh question. Seventh question is okay. So water in a 5 centimeter deep pan is observed to boil at 98 degrees Celsius. At what temperature will the water in a 40 centimeter deep pan boil? Assume both pans are full of water and take density of water to be 100 kgs per meter cube. Okay. So again, this will kind of, let's see if we can solve this using this graph. So this graph says that when you have a 5 centimeter deep pan, right? At the bottom of the so you know this fact, this for the fact, right? Boiling happens at the bottom of the pan where the heat addition is the like it is the closest to the stove, right? So if you have a pan, boiling happens here. The pressure is generally higher, so the pressure here will be P plus rho GH, right? So the essential idea is this is what they're trying to say, that Tsat at P equals to P naught plus rho G, let's say H1, or let's say 5.005. Let me put it this 5 centimeters, right? So 0.05 is 98 degrees Celsius. And then they are kind of interested what happens if it is a 40 centimeter thing, which is 0.4. So now we know the pressure has increased. Okay. So again, it cannot be 88. So that one goes. Will it be 108, 120? Let's see that. So now, how do we do that part? How do we figure out which of these three other values it is? Okay. Uh, okay. So the correct way to do it is we first need to, from this equation, we first need to find out P naught. So we will have to use steam tables now. So let me open that steam tables so that we can quickly do this question. First, we need to figure out P naught because we are not sure what the ambient pressure is. Okay. Atmospheric pressure nearby, we don't know that. So how will we do it? We will first see what is the saturation pressure corresponding to 98 degrees Celsius. So for that, we will have to first calculate here. We will have to first calculate using these two quantities. Let's calculate this term. Okay. So insert table. So we are aware of the fact that at Tsat and Psat values. So let me first also check what table am I using? Am I using the right table? So this is the saturated water table, okay? And these are the entries for it. We'll look at the entries of 95 and 100, okay? So this is 95 degrees Celsius. I'll put degrees Celsius here. And kilopascals here. I think kilopascals is the unit they have used. 95 and 100. What are the values? 84.61. Let me take 84.61. 84.61. And then you have, for 100, you have 101.42, or 101.42 is okay. So what will be 98? Can anyone tell me quickly? You'll have to use a calculator there. This is a simple interpolation exercise. 4.61 plus 3 degrees. The difference divided by 5 into 101.42 minus 84.61. So we are kind of getting it to be 94.69. 94 point, I'll take 67 only, 94.7. Okay. So we know that P naught plus 0.005 into 10 to the power 3 times G I will take as 10 is 94.7. Let me just quickly see if it is kilopascal or not. It's kilopascal, okay? So into 10 to the power 3, right? Times 10 to the power 3. So you see there's a cancellation that we can quickly do. So we can quickly also find P naught there. Okay. So now if I cancel this 10 to the power 3 from both sides, the P naught that I will get will be in kilopascals. Okay. And if I take this thing on the other side, this is 0.5. So you do 94.2, right? P naught becomes 94.2. So now what is P naught plus 94.2 kilopascals? Okay. So then P naught plus 0.4 rho G is what? 94.2 plus 0.4 into 10 to the power 3. Again, you note that this rho GH is in pascals. So we have to, when you are adding it with kilopascals, this 10 to the power 3 cancels out. Okay. So 0.4 into G, which is 10. Okay. This will become 98.2. Okay. Now I know that my PSAT is now 98.2. So I'm now based on these two values, I need to calculate TSAT. Okay. Make sense? So let's do that. So let's take 84. Now we need to interpolate using PSAT values to find TSAT. Okay. So 84.61 plus 101.42 minus 80, not 101, minus 98.2. So 84.61 plus 98.2 minus 84.61 divide by this, divide by the difference of 101.42 minus 84.61 into to what? Let me see. Wait. So it should be 95 plus, so right, 5. Yeah, this comes out. So basically what I am doing in this final step, let me just quickly type that part so that nobody gets confused. Essentially now I'm calculating and saying 95 plus from the fraction, remove this. So now what I have done is 98.2 minus 84.61 and 101.42 minus minus 84.61 into 100 minus 95. Okay. This is the interpolation that you will need to require and you will get something close to 99. Okay. Acha, tell me one thing. Was there a quicker way to solve this problem? If this problem comes in your exam, are you going to do this? Were you required to do this calculation, this interpolation? See, up till here, we actually needed to do all those things. We needed to find out P naught and calculate this P naught plus 0.4 G. So we needed to find it 98.2. But since once we got that 98.2 is the pressure, boiling pressure in the second conditions, we could have just quickly figured out the answer without solving this equation. Okay, how we see this 98.2 is kilopascals, right? This value lies between these two numbers, 84 and 101. which is between 95 and 100 degrees Celsius. So you know that the saturation temperature should also lie between these two values, and there is only one value which lies between 95 and 100, which is 99. So that is that this was a little quicker. This step which could have been avoided. That is what I'm trying to say. Okay. Anyways, let's go to another question. Uh, yeah. So the other question is, a rigid container is a volume is given of that rigid container. Uh, you have been given the component also, the species, which is R134A. It's a refrigerant. The mass is given, initial temperature is given. The container is then heated until the pressure 200 kilopascals. Determine the final temperature and initial pressure. Okay. So first let's figure out initial pressure. Okay. So once you have the mass and volume, you have the density with you, okay, or the specific volume, okay, specific volume, right? So the specific volume, initial specific volume is how much? Small v is how much? 0.1348 meter cube divided by kg, okay? And another thing which you have is T is minus 40 degrees Celsius. Okay. Now, based on this, you can quickly find out the initial pressure. So let's do that. In this property table only, we have to do it. So first we need to go to the table for R134A. See, R134A table we have found. T saturation minus 40. What density now? Acha, now do you know how will based on this property table, how do you find the initial pressure? Anyone, would you like to volunteer, help me out here? Okay, so when you are using property tables, see, when you're using property tables, essentially what is this table about? What is this table? What is it telling you? It is telling you nothing but this plot which we had, okay? This saturation dome plot we have, no? This is what the plot tells you. It gives you in different coordinates this line. It is essentially telling you this line. This line. Okay, it also tells you in terms of PV, right? So now to actually figure out the initial pressure, first you need to figure out in which region of your let's say it's subcritical. So we are not interested in this part of it. Generally, let's say we are not, or let's make it more general. So first we need to figure out what region is this. What do you say? And let me make another plot here. Let me make another plot. So one is PV, one is temperature entropy plot. There is another plot which we can have, which I showed, right? Phase diagram plot for something like this, and you will have this and this. So on a pressure temperature diagram, you need to actually figure out in which kind of region are you in, okay? Are you in this part of it? Then there will be a region. Are you in this part of the region? All those things. So for that, we know that how densities change across the saturation dome. Okay. So you see that if it were a liquid, then the density, if it were in the left part of the saturation dome, then the density of the liquid, or the density of the state or the density of the system will be lower than the liquid density. If it is on the gaseous phase, on the right hand side of the saturation dome, then the density of the system will be higher than this value. But what is the density value? 0.13, which lies exactly between these two, what do you say, these two values. So you know that with T temperature of -40, you know that the P sat will be 51.25. So you don't need to do much there. Okay, you quickly have the, what do you say, the saturation pressure. So you know that the answer to this question will be amongst these two. Okay. Now the second question is, see, we can't forget that we have not any calculated anything using this data. We have to first calculate the quality of the system also, how much gas it has. Okay, that we have not calculated yet. Can we quickly do it? Yes, we can quickly do it because we have a formula of, what formula do we have? We have this formula. I'll write this formula for you. You must be well aware of it. Nothing new in it. V equals to Vf plus what is it? 1 minus x. No, it's x VFG, right? So how do we get this? We essentially say that V is equals to uh, x times of VG plus 1 minus x times of VF. Now VFG is VF minus VG. So now which is, so essentially you get, if I remove this space, then essentially I have plus x comma VF minus VG. Okay, so this becomes VFG, and so you get the above formula, right? I think we'll also have VFG is not there. No ways, not a problem. We can write this expression as I had written earlier in terms of VF and VG. So V is 1 minus x VF plus x time VG, right? So quickly let's calculate what x is from this equation. So V is 0.1348 is something that I don't know, but VF is something that is given to me, which is point this thing, whatever it is. We write that thing down plus x times of what is this value? This is right, or right. I will not like to use this formula, right? Let me use this only. So then this becomes simpler way of doing things. So this becomes 0.1348 is 0.307054 plus x times of, you put this and you subtract this, that is 0.7054. In all consumption kind of sense, you can actually neglect this part because you see this is a very small quantity. So then let's calculate this. Even in this case, there are 3 zeros, right? We can also neglect this part of it. Roughly, I'm not doing the maths behind this. You can be exact and do all this to find the exact x quality, right? But roughly, if I have to calculate it comes out to be 0.36. It will be around 0.37. Okay, so x comes out to be roughly 0.37. Now, why do we need it? We will need it to find the final temperature. So the container is then heated until the pressure of 200 kilopascals. Okay. Again, note that the density of the system will still remain same. So you are still dealing with 0.1348. So we'll have to do another the same thing for the pressure of saturation pressure of 200 kilopascal. See if it is in the saturated dome or superheated dome, superheated region or saturated subcooled region. So that we'll see at saturation pressure of 200 kilopascals. So I think, yeah, this is, so let's look at this entry. Okay, let's go into the, now look at the densities. See, your density of specific volume is higher than both of these values. This is for 134A at 200 kilopascals. This becomes higher, okay? So both VF and VGs are lower than your, what do you say? Your specific volume, okay? Which means what? That you have gone into the superheated region, right? Your volume has gone much higher than the saturation volume, saturated vapor volume, right? For the same amount of mass. Okay. So now we have to go into the superheated table. These are saturated tables. Now in the superheated tables, this is the superheated tables. Okay. So we go to point. So we are at the 200 kilopascals. So we will have to look at these. We will have to interpolate between these two tables. Okay. Uh, Now the pressure is known to us, so we will have to. Okay. So we'll have to interpolate between entries of this table and entries of this table to calculate and like to come up with an entry of what do you say, with a table explicitly for 200 kilopascals. Okay. Uh, and in that case, we'll have to find how V varies with temperature. So you see in this case, the entries are much higher than, so our density, our specific volume is 0.13. Okay. And this here, look at here. So now what do we expect? Okay, now let's look at, we have two pressure, what do you say? We have two pressure limits, right? We know that our, so our specific volume at P equals to, now we know that this is, so one thing which we know is X final is 1, okay? This is in superheated region, okay? Now, the other thing which you know is the specific volume at pressure of 200 kilopascals, or right now I'll write it as 0.2 megapascals, must be, now you tell me, what should the relations be? Now you guys have to answer me, okay? One pressure is this, and then another pressure is 0.1 megapascals, okay? These are the two tables, right? 0.06 and zero point 0.1. There is a comment. Okay, what is the general formula for interpolation? This is something which you can, so the general formula is generally when you're interpolating anything, uh, when you're interpolating anything, let's say you know values on a x-axis, right? So if you know entries, so you will have generally, this is the interpolation technique, okay? You draw a linear interpolation. You have 0.1, you have 0.2, but you want to know the value at somewhere here, okay? So you know x1 comma y1, and you have x2 comma y2, and you need to find, and you know either x or y of this point, right? Let's say we know x value, then what is this y value? So how do you find this? So we use the x equation for line for the, what do you call it? Line equation, okay? I don't know what it is called. So what do you say is, you write it as y minus y1, and take this. x minus x1 is the same thing because it is a linear equation. So so this is a line. So the slopes is constant. So you use this. Now what this will give you is, this essentially gives you is that y equals to x1 plus, sorry, y1 plus y2 minus y1 divided by x2 minus x1 times x minus x1. Okay, now let me just quickly apply the same thing on the case we had done these things, right? What had I done? Let me just quickly show it to you so that this becomes clear to you. When we were trying to, so we earlier didn't know this, right? We knew all this data except this one. So we wanted to calculate this value, right? Is there anything else? Any other comment? Right. So as I was saying, so let's say we wanted to find p sat, right? So this is how I will apply it. Okay. So now I want to find p sat at 98 degrees Celsius. How do I calculate it? I will say I'll pick one p sat value. This becomes p1. So this becomes 84.61 plus 101.42 minus 84.61 divided by 100 minus 95 times x, which is 98. Note, this will be 98 minus 95. So does this make clear? Does this make the interpolation procedure clear, Hassan? Or do I also demonstrate the other interpolation that we did in the previous problem? It is clear. Okay, fine. So let me go back to what we were doing before. Now, in this case, Jyotirmay ji, I would welcome if you can tell me what follows. Is this a greater than? Is this lesser than? What is the relation between these two quantities? And then also between these two quantities. This is 0.1. Wait. I'm not taking the right values. This is 0.4. This is 0.2. Oh, wait. So we have the table explicitly for 0.2. Okay, in this case. This is 200 kilopascal. This is the table that we are going to use. 200 kilopascals is 0.2 megapascals, right? So the table is correct. But let's say I want to calculate, this is 0.1 and this is 0.3. Can you at least suppose this table did not exist? Suppose this table was not there in the property tables. What would we have done? We would have to interpolate between two tables. Let's say the actual pressure was 0.22. Then we'll have to interpolate between these two. But now you tell me, what will this relation be? What do you expect? If pressure increases, our specific volume is supposed to decrease, right? Because it gets compressed, so our volume is going to decrease, and for the same mass, so our specific volume is expected to decrease, right? So that is how we interpolate, right? Okay, so that is one thing. But in our case, you see that we already have a table, and we had the density value as 0.1348. Okay, so 0.1348 lies somewhere here. So 60 and 70, somewhere between 60 and 70. And what 60 and 70, there is only one entry, which is 66.3. So we can quickly, without solving the interpolation, quickly answer it. But if you do it, you should get 66.3. Okay. That is the gist of the problem. Okay. Let me share the 8th question. No, this is the 8th question. So let me share the 9th question. We're almost done with this. Let me share the 9th question. So you need to note that, okay? So dealing with property tables, you need to have a feel for how the properties vary with pressure and temperature in different regions, in superheated region, in subcooled region, and so on, okay? Anyways, a rigid tank with volume this contains this much saturated liquid vapor. Uh, Saturated liquid vapor, mixture of water at 90 degrees Celsius. Now the water is slowly heated. Determine the temperature at which the liquid in the tank is completely vaporized. Now in this case, again the same thing. Let's calculate the specific volume. What is it? 1.8 divided by 15. 15 is 30 divided by 2. So times 2. And this becomes 10. This becomes 0.6. So 0.06 into 2. So 0.12, right? So 0.12 is the specific volume. Now it says that it is a saturated liquid mixture, so it also tells you that the quality is less than 1, and the temperature it has told you that T is 90 degrees Celsius. Now what is it asking you? It is asking you that now that you have slowly heated it, it's a rigid tank. Note that it is a rigid tank, so the volume is not changing. Okay, these are important cues to solve the problem. Even in this case, it was a rigid container, so volumes are fixed. That is why our density was fixed. Okay, note that. Um, Now the water is slowly heated. Okay, and the tank temperature, it is trying to identify at what temperature will the liquid completely get vaporized. So what are we expecting here? Okay, let's also look at what is going to happen on the TS diagram, or let's say P. What diagram would you like to look at it as? Let's say PV. Okay, maybe PV is a more comfortable plot for you guys, right? And these are isobaric lines, right? This is T equals to constant, right? Okay, now you're heating it. So it will be somewhere, let's say here, right? When you're heating it, what should happen? Specific volume is fixed. Let's say it is somewhere here, okay? Let's say it's somewhere here. What will happen? It will heat up. Now, when you're heating a system, should it go up or should it go down? Jyotirmay ji, can you answer this?
Mm. Please.
Should it go up or should it go down? We know that the specific volume is a constant, so it is going to move in this line, okay?
Yes.
This is, but is it going to go up or down? That is the question. And the hint is already there. It says you have to find the temperature at which the tank is completely vaporized. From the figure, we are kind of clear that the vaporization can only happen if this thing moves up, right? Can it completely vaporize if it goes down?
Mm. Well, during the phase change process, the temperature will be constant, but after that,
See, the temperature cannot. No, no. Why? Acha, okay. Why do you say the temperature has to be a constant?
no, during the phase change process, that is the latent process, latent.
But see, that is the only that is see, temperature remains constant if it is a isobaric process.
Okay.
if the process you're undergoing is your pressures are constant, then your temperatures will also remain constant. But this is not an isobaric process. This is an isochoric process, isn't it?
Yes, yes. It's the volume is constant. Okay.
Right? So now actually you realize that we are going to traverse. Suppose when you're heating, let's say if it were I don't want to put anything into it, but essentially we are going to move in this region. We are in this part of it, in the saturation dome. And because it's a isochoric process, we can actually constrain ourselves to this single vertical line. Now my question is, how do we know that we are going to move up? That is the question I'm posing. Hassan, would you like to answer that? Or you would you like to say that you don't know, or uh, anything, like any comment you have, or some intuition you have, like probably why? I'll tell you why. So you are heating it, right? You know that higher isotherms are like this, right? Temperature increases a lot in this direction. Does that make sense now? When you're heating it, you're expecting the energy of the system to go up. So you expect the system's temperature to go up, and that is why this should go up. If I, let's say, draw this same diagram on a TS plot, how would that look? This is an isobar. I'll draw an isobar. Okay, so this is P equals to constant. And we are somewhere here. Okay, there are isotherms or isocores on this curve. Okay, so it will go somewhere like this. Okay, let's visualize how an isotherm looks. Okay, on a TS plot. I don't know if temperature entropy has come in. I don't know that part. Let me check. But generally, we draw PT, right? In the early chapters, we draw PT rather than TS. We draw PT. No, not PT. TV. We draw TV. Temperature and specific volume. That is what we draw. But later on, you will see temperature. This thing. See, these are what do you say? Isobars, right? So roughly, we are going to move somewhere like this. Say you are somewhere here, you're going to move up along this dotted line, let's say. Okay. So, okay, so that is the question. Now, let's come back to this question and solve it. So, we know the density. So, we know something about the initial um, conditions. We can actually calculate. Can we calculate? Yeah, we can calculate the quality of this using the density. What do you say? Using the specific volume. But we actually don't need to do that because we are told that the tank is completely vaporized. So we are told the final condition, our quality is one, right? X final is one. Okay, that is told to us. And so essentially, we just need to find at what temperature, So essentially, what are we asking? We are asking T. Uh, we are asking essentially we are saying that V saturate Vg at T is 0.134, no, 0.12, and we need to find this T. Find T such that. Is this clear? So we actually need to go to the property tables for that. Is this statement clear? We need to find a temperature for which the specific volume should be equal to the saturated vapor volume. Make sense? So we go back to the property tables for the water. Mm. And we look at the temperature based property table, and we look at the saturated, what do you say, vapor volumes, specific volumes. So you see, you at very low temperatures, you have a very high specific volume, but as you go lower, your specific volume starts to decrease. Now you're somewhere close to 1.2, right? Which is roughly close to 110 degrees Celsius. So let me just check if that is the answer of the question. Is it 110? Let me just quickly check because property table says so. The options, what are the options do we have? The option is 203. Let me, have I done this incorrectly or what? 1.8 divided by 15 is 0.12. Density is fine. Now the water is slowly heated. Determine the temperature when the liquid in the tank is completely vaporized. So just quickly we check. Vg is 0.12, right? 0.12. It's not 1.2. Oh, sorry, I'm sorry. So it's 0.12. So which is somewhere between, if you see, it is close to 200 degrees Celsius, right? 0.12. So the option that we will have should be around 200 degrees. So 203 will correspond to exactly 1.12. I made a mistake there. So this option will be there. Okay.
So,
Yeah.
sir, I had a doubt that whether we can solve all the problems using the interpolation method or are there some exceptions in it?
What do you mean? What do you mean? So can you elaborate?
So I mean to say that for the question, for this same question, we can use interpolation method by finding specific velocity at the gaseous state and then put the values and corresponding to that using the temperature table and find the table,
Okay.
find the
Are you, let me, if I understand, if let me try to paraphrase what your question is. Are you trying to say that, sir, so what I'll do is I'll go to these superheated tables and at some so essentially using these tables, I'm going to interpolate and find a value, is it?
yes, sir.
See, the problem is, in some problems you might require to do it, but look at the question that we have at our hand. It says determine the temperature at which the liquid in the tank is completely vaporized. They are specifically looking at the superheated vapor line. So this they are kind of looking at this saturated vapor line. Okay, they are interested at this line. So while you can use that table, see, even that table, superheated table, has that. I will show you. See, these superheated tables have these pressure versus temperature values. See, for point 1, point 5, they have a temperature value. So P versus T is there, right? So you can do that, and they have saturation. So you can, in principle, use these table values also. My only suggestion to you will be, see, if you understand the physics of it, if you understand what is going on the plots, if you understand what is going on, no matter what table you use, the answer will be the same. It cannot be different. Okay, but
Yes,
you
sir.
have to be sure. Yeah, so you can do it. Okay, you can use this table or some other table. The answer will not, should not change, and it will not. Okay, that is there. Sometimes it is a little, sometimes it could be quick. It could be a smart, like some table will give you a faster answers. For example, I showed it to you, no? We were solving an interpolation problem which we actually didn't need to solve. In this example, we kind of were able to see that the pressure was somewhere between in these two values. So we knew that the answer will also be between these two numbers, 95 and 100. So sometimes it is actually quicker to not quickly see which table it is better or not. Some see even in this case, even in this tables, there are two tables. Okay, the same table is plotted different. Like this is the saturated water table. Okay, there is a temperature table and there is also a pressure table. Okay, if suppose you're given a pressure value and you're using the temperature table, then that will make your life harder. Okay, so you have to be also wiser in choosing your tables. That is also something that you will have to take care of. But I don't think it's okay, right? You, that is a trivial thing. You can take care of that. So yeah, that is there. Okay.
Okay,
So
sir.
now yeah. So now let me close this session for now, and we'll meet tomorrow. Or like we'll meet next time. There are one, two more questions left that we can discuss. Those are on the similar lines. Let me do that next time because it's already 2 hours. And we'll meet next time. Okay, then. If you have any questions, we can discuss them now, or I'll close.